All right, here the recording in progress. All right, so we're finishing up 7.3. I should be able to do that fairly quickly, and I'll sneak in a little bit of 7.4, and we'll see how it goes. Okay, I'm actually going to throw one problem out from the homework, so please make a note of it. 7.3, let's skip problem 19. It's a little bit too involved, I think. So 7.3, skip problem 19. Okay. All right, so again, we're looking at 2 days per section, 2 days for 7.3, 2 days for 7.4, and so on. This Friday, we have another quiz. Then the Friday after that, the 24th, will be our second exam. And now that you've already seen one exam, you know how I'm going to do all the exams. Again, a reminder for the exams, you have to actually show up then. These sessions, lectures, so-called, they're optional attendance. As you know, I don't take attendance. You can always watch the video later, but you have to show up for the exams. Okay. All right, so let me go back and finish up 7.3, of which I've either done many of them or given you hints on a lot of them. And the only other one I wanted to do in its entirety was problem 29, last one there. Okay, and please notice the little hints I gave you. 17, just do a U substitution, right? You don't need to do this by trig substitution. Just do U equals x squared minus 7. Du is 2x dx. Do 25 like I showed you 23 star. And let's see, hint for 27 was to add 1 and then quickly subtract 1. So make it x squared plus 2x plus 1 minus 1, which factors into x plus 1 squared minus 1, and then do a substitution, t equals x plus 1. Okay. All right, so the last one I was going to do in its entirety is 29. Okay, so 29, integral of x radical 1 minus x to the 4th. Okay, and then that would be the last one I was going to show you there. So let me show you that one. Okay, so here's the integral. Again, ignore any dates I have here. So x, 1 minus x to the 4th. Okay, so the game you play here is sort of like this. You sort of say to yourself, I wish this were x squared, because if I had x squared here, I can then do a U substitution. Seems I have trouble focusing here. There we go, I think. Well, seems to go back out of focus. Okay, so what I'm going to do here is make this into 1 minus x squared squared. So I want the x squared because the derivative of x squared is almost x. And by almost, I mean I have to multiply by a constant. So I'm going to transform this into a radical 1 minus t squared. If it looks like radical 1 minus t squared, then I can use the table. I can then use this thing, right, on page 486. So I write this as 1 minus x squared squared. Let u equal, t equals x squared. I want to save my u in case I need it for later. So t equals x squared. dt is equal to 2x dx. So there's the x. There's a dx. I need a 2. Remember, you can multiply a constant inside and a reciprocal outside, but you cannot do that for variables. So for instance, you're not allowed to put an x inside and a 1 over x outside. That does not give you an equivalent integral. Right, so t equals x squared, dt equals 2x dx, put a 2 inside, half outside. So the next step, this is going to become 1 minus t squared. 2x dx, 2x dx is my dt. So I now have 1/2 integral of radical 1 minus t squared dt. All right, so 1 minus t squared. So 1 minus t squared, that's 1 minus x squared. That looks like the first one. X equals a sine theta, or t equals a sine theta. What's my a this time? 1. Okay, so t equals sine theta, dt equals cosine theta d theta. So right here, I'm going to put sine theta. Right here, put cosine theta d theta. So I now have 1/2 radical 1 minus t squared sine squared theta cosine theta d theta. Okay. And now what is 1 minus sine squared theta? Cosine squared theta, whose square root is cosine theta, if theta is in a nice interval, and it is, it's intentionally picked that way. So this is cosine theta times another cosine theta, so I have cosine squared theta. So now I just integrate cosine squared, use my identities, put it on your cheat sheet if you wish. Cosine squared is 1 plus cosine 2 theta over 2. All right, take out the 2, bring it with this 2, so I have a 1/4 in front. Integral of 1 d theta is theta. Integral of cosine 2 theta is sine of 2 theta times 1/2. Again, chain root in reverse. Opposite of what I do for differentiation. Right? If I differentiate cosine 2 theta, I would go negative sine 2 theta times 2. Right? So instead of multiplying by 2, when I integrate, I divide by 2 or multiply by 1/2. So theta plus 1/2 sine 2 theta plus c. Or again, double check by differentiating this, right? Remember, anytime you integrate, you can always say, did I do it the right way? Take the derivative. Derivative of theta d theta is 1. Derivative of 1/2 sine 2 theta is 1/2 cosine 2 theta times 2. That 2 knocks out the 1/2. All right, this is sort of correct, but I need to do my triangulation, so I don't want a double angle. Okay. Do I have any formula from trig for the sine of 2 theta? Yes. You might recall from trig, sine of 2 theta is 2 sine theta cosine theta. And you're welcome to put that in your formula sheet also. Remember in trig, you had the double angle formulas. One of the formulas was, so I'm leaving this alone, leave that alone, leave that alone. Just changing right here. Sine of 2 theta is 2 sine theta cosine theta. Put that on your formula sheet if you wish. Okay, and very conveniently, the 1/2 cancels the 2. So right now I have 1/4 theta plus sine theta cosine theta plus c. And integration is done, but you have to watch out. There's a very big tendency for students to just say, oh, that was some heavy duty integration. I'm glad I'm finished. I'm done. But in reality, you're not done because, again, look at the way your answer is. The answer right now has theta, and that doesn't make any sense, right? Because your original problem didn't have any theta. The original problem was x. So I can't leave it like theta. I need to change it to x. So is there some relation between x and theta? Oh, yes, right here. T is sine of theta. And then I do my triangle stuff. So sine of theta is t, which I'm going to write as t over 1. Okay. Sine from my SOHCAHTOA, sine is opposite over hypotenuse. So I draw myself my triangle. I go opposite is t, hypotenuse is 1. And then for the thing behind my finger, I'll just use the trade secret. I know it's going to be some funny square root. I'll just peek back where to go over here. Radical 1 minus t squared. Double check. Is it true that a squared plus b squared equals c squared? Right? So what is this thing squared? 1 minus t squared. What is this squared? T squared. What do you get when you add them up? 1, which is equal to 1 squared. So it definitely works. And furthermore, I notice I have a theta here. So if t equals sine theta, then theta is inverse sine of t. Okay, so I'm ready to substitute back. So the original integral is 1/4 theta. So I now know theta to be inverse sine of t plus sine theta cosine theta. So sine is what? Opposite over hypotenuse. So t over 1, just write t, times cosine theta. Cosine is adjacent over hypotenuse. So radical 1 minus t squared divided by 1. Well, of course, if you divide by 1, you don't have to put it. So radical 1 minus t squared. Okay, so here's my 1/4. This is theta. I think I should just go ahead and write theta here for you. Okay, so this matches this. Theta, inverse sine of t, plus sine of theta is t. Cosine theta is radical 1 minus t squared, right? So here's theta. Sine is opposite over hypotenuse, t over 1. Cosine is adjacent over hypotenuse, radical 1 minus t squared over 1. And furthermore, I can't even leave it with t. I'm going to switch back to x. So t is equal to x squared. So the last thing I need to do is everywhere I see t, change it to x squared. So just make that an x squared, make that an x squared, make that x squared squared. And I finally have it. So final answer is 1/4 inverse sine of t, which is x squared, plus tx squared, radical 1 minus x squared squared, x to the 4th, plus c. So at long last, here's my solution. Okay. And of course, it's not that unusual that my final answer would have a radical 1 minus x to the 4th if the derivative of this does indeed come out to be something involving radical 1 minus x to the 4th. That's not surprising at all. And you can see it is. Okay, so that's that. So again, if you feel like checking this, it's going to be quite a bear. But the derivative of all of this stuff, if done properly, should come out to be that. I'll leave it to you to check on that if you wish. Okay. Okay, so I'm officially done with section 3. So I'm on par for today. I still have more than half the time. So I'll sneak in some of 7.4 and we'll probably still end a little bit early. Okay, and I notice there's a buffer day coming up next Thursday. So just like the first test, I'll probably save some of that for questions and answers, but we'll see how it goes. Okay, so I'll introduce some of 7.4. But the main ideas for 7.3, again, is for 7.3, page 486. You want to see which of these 3 scenarios you have. Okay. Put it on your formula sheet. If you have square root of a squared minus x squared, square root of a squared plus x squared, or square root of x squared minus a squared, then you pick these. Okay, you don't really need this stuff, cover this stuff. Okay. This just tells you have a quote unquote nice angle. Okay. And you can put these if you wish. These are the identities that are involved, right? This is a variation of sine squared plus cosine squared equals 1. This is the standard identity, 1 plus tangent squared equals secant squared. And let's see, if you subtract 1 on both sides, you get tangent squared equals secant squared minus 1. Okay, so you just pick the right one on that. Okay. All right, so I'm going to introduce 7.4, something called partial fractions. Okay, some of you may have had some partial fractions before, but if you've never heard of it, that's okay. I will lecture assuming you've not seen partial fractions. So if you've already had partial fractions, great for you. You can hopefully just relax a little bit. You've seen it, but I'll lecture assuming you've not seen partial fractions. Okay, so this section, there's going to be some long division. The first problems that we'll do involve long division. And first, let me show you the homework for those of you who don't have it. So 7.4, 1 to 25, odd, 39, 41, 43. So let me get that to you. Okay, so page 501. So the highest grade to go was 43. So let me show you the homework for those of you that don't have the book and aren't getting it. Oh, now hold it like that. You can see up to 43, I think. Is 43 our highest problem? Yeah. Okay, so you can see that. You don't need to see the evens over here because we're not doing any evens. Okay, so that's up to about 19. And that gives you the bottom. Okay, I think we're good there. All right, notice what we're doing now. We're basically having rational functions, polynomial divided by a polynomial. Okay. Again, you might say to yourself, I wish there were such a thing as a quotient root, but unfortunately there is no quotient root for integrals. There's a quotient root for derivatives. You always do the same thing, but there's no quotient rule for integrals. So that's why we have to spend time doing all these tricks of the trade, so to speak. Okay, first thing I'll start off with is something like number 7, which is essentially a review of polynomial long division. Okay, if I can divide this out and get some polynomial plus a remainder involving x minus 1, then I know how to integrate that. Okay, so let me set you up with number 7 as an introduction. So long division, integral of x to the 4th over x minus 1 dx. So do you remember long division from your algebra, right? So in fact, most of the problem here is a long division. Once you get the long division, the integration is simple because you're going to have a polynomial plus some remainder. Okay, so for polynomial long division, you might recall from your algebra, you have x to the 4th. Now, if I have an x to the 4th, when I do my long division stuff, I have to have x cubed, x squared, x, and a constant. And if I don't have them, put them down with a coefficient of 0, right? So recall, if I just divide x to the 4th by x minus 1, I got to go x to the 4th plus 0x cubed plus 0x squared plus 0x plus 0. Remember that? And then we do the polynomial long division. So let me review how does polynomial long division work. Okay, so take the first thing here and the first thing here. So from the pen on the left, what do I multiply x by to get up to x to the 4th? How do I go from here to here? I multiply by x cubed. And so I put up x cubed in the x cubed column. So there are dedicated columns, right? This is meant for x to the 4th. This is all x cubed. This is x squared. This is x. These are numbers. Now you might recall I take this and multiply it by this whole polynomial. So x cubed times this whole thing. So x cubed times x is x to the 4th. X cubed times -1 is negative x cubed. And you might recall the operation is subtraction, just like when you did long division of numbers, right? When you got to this stage, you subtract. So I subtract. That minus that is nothing. 0 minus a minus 1 is 1, so x cubed. Bring down to 0x squared. Do it again. Okay, so now I take this to this. So from the pen on the left, how do I go to the pen on the right? What do I multiply x by to get x cubed? X squared. So I put plus x squared. Now you take x squared times this whole thing. So x squared times x is x cubed. X squared times -1 is negative x squared. Subtract in parentheses. That minus that is nothing. 0 minus a minus 1 is 1. So again, x squared. Bring down to 0x. Do it again. Okay, so remember doing this stuff in your algebra class, perhaps? Algebra 1, maybe? Polynomial long division. Okay, now, how do you go from x up to x squared? Multiply by x plus x. Now you go x times this whole thing. X times x minus 1 is x squared minus x. Parentheses, subtract. That minus that is nothing. Again, 0x minus a minus x, that's like plus x. So x, bring down to 0. And I do it one more time. And this one more time, I know it's going to be the last one because I reached the end. Just like when you do long division of numbers back in grammar school, right? Long division, so when do I get to stop? Well, you get to stop when you reach that last digit. So same thing here, I reached the end, so now I can stop after this last one. Okay, again, look at the first thing here, What do you multiply x by to get x? Well, 1, so plus 1. Now 1 times this whole thing is just x minus 1. Subtract, x minus x is nothing, 0 minus a -1 is 1. So my remainder is 1, so I put plus 1 over the original divisor. And again, that's just like long division of numbers, right? You have a quotient plus a remainder. So this thing goes on top of a fraction, this thing goes on the bottom, right? Just like in arithmetic where you go 5 and 2/7, right? The divisor was 7, the remainder was 2, so you have a quotient and plus remainder over divisor. Okay, so x to the fourth divided by x minus 1 is all of this stuff. Right, and a way to double check that, of course, is if you were to multiply that by that, okay, x minus 1 times all that stuff, and then you add on the 1 over x minus 1, you should get back x to the fourth. Okay, you can check it or not, but see, that's it. Okay, so let me just run through the long division process quickly for you again. So first thing here, x cubed. Multiply x cubed times that whole thing, subtract. Repeat the process, x squared, x, 1. Okay, you got to this step here, x minus 1 to x. Finally, x times what gives me x? Well, plus 1. 1 times that is x minus 1, subtract, the remainder is 1. So x to the fourth over x minus 1, the original, this thing, I can now write as all of this. But now this is very easy to integrate. That's the whole idea. Okay, so that's polynomial, 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 ln. So x to the fourth over 4, x cubed over 3, x squared over 2, x plus natural log absolute value of x minus 1 plus c. And there we go. Good. All right. I'm going to have you ignore this. Page 44 bottom, that does not apply to our book. So maybe I should just cross this out. Okay, so this is not something in the text. This is just my own work. Okay, so timeout, as it were. Let's recall in algebra 1, suppose you were given 2 over x minus 1 minus 1 over x plus 2. And the question was, combine them, right? Do the subtraction. That minus that. So you've all seen that in your algebra class. So let's review that. You need a common denominator, right? So on the left side, you multiply by x plus 2 over x plus 2, right? And then this side, you multiply by x minus 1 over x minus 1, right? It's like this side needs that, and this side needs that. It's no different than if you have 2/5 minus 1/3, right? 2/5 minus 1/3. The 3 needs a 5, and the 5 needs a 3 to get a common denominator. So same thing here. To get a common denominator, x minus 1 needs to have an x plus 2 plus over x plus 2, and x plus 2 needs to have an x minus 1 over x minus 1, right? Same principle. So now that you have a common denominator, you can work out the top. So that's easy. 2x plus 4 minus x plus 1. So x plus 5 over x plus 2, x minus 1, right? So you should all be familiar with this. Partial fractions goes backwards. You probably did not do a whole lot of that in your algebra class. Okay. Suppose I start off with x plus 5, I sneak in the 1 later. Okay. X plus 5 over x plus 2, x minus 1. Can I bring it back to a over x plus 2 plus b over x minus 1? That's the idea behind partial fractions. Okay, so one more time, in your algebra class, you probably did quite a few problems like this. 2 over x minus 1 minus 1 over x plus 2, subtract, get a common denominator, blah, 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 comes out to be x plus 5 over x plus 2, x minus 1. You can all do that. Okay. You probably did not do too much of going backwards, which is called partial fractions. If you have done it, great. Okay, then just follow along. Can I go backwards? If I start with x plus 5 over x plus 2, x minus 1, how do I bring it back to a over x plus 2 plus b over x minus 1? Now, in this case, we're kind of cheating. We already know what the answer should be. A should be 2 and b should be -1. Right? But that's the concept behind partial fractions. Okay, but let's pretend I didn't just run through this stuff, right? And we didn't know that it's supposed to be, oh yeah, 2 over x minus 1 over x plus 2 or whatever, right? Suppose the original problem was, okay, x plus 5 over x plus 2, x minus 1. Rewrite it so that it looks like this. And actually, the way I wrote it, let's see, the -1 should actually be here, right? I actually switched these, I guess, but anyway. So I wanted to get a -1 here and a 2 over here to match the original. So how do I do that? Okay. Well, it starts off kind of like what you did in algebra. Okay, so start from here. Even if you got A and B, you know there's some constants. Just go ahead and do what you did over here, meaning multiply this side by x minus 1 over x minus 1. Multiply this side by x plus 2, x plus 2, right? So A over x plus 2, B over x minus 1. Multiply this side by x minus 1 over x minus 1. Multiply this side by x plus 2 over x plus 2. So again, I have a common denominator. Whoops. X plus 2, x minus 1. Go ahead and multiply out the top. So ax minus a plus bx plus 2b, right? Now I gather like terms. So how do I do like terms? There's so many letters here. Okay. A and B are treated as constants. So if we pretend they're constants, okay, these two both have an x. So factor out the x, a plus b quantity x. Okay. Do you agree that's the same as ax plus bx? That and that. Plus parentheses, the stuff that doesn't have x, -a plus 2b. So this is the same as this. Right? So one more time, from here, multiply this side, top and bottom, by x minus 1. This side, top and bottom, x plus 2. Work out all the top. Group the x's and the constants. Constants meaning it doesn't have an x. So these two group because they have an x, a plus b. These two group because they don't have an x. And now I set it equal to the original x plus 5, which I'm going to write as 1x plus 5. All right, so now the goal is this. Find a and b so that this fraction matches this fraction, right? So I got to get this fraction to match this fraction. Well, the bottom's already the same, right? I need this to match this. The bottom's already the same. So I need the top to be the same. In other words, I have blah, 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 x equaling 1x, and this blah, blah, blah equals 5. That's going to be true if a plus b is 1, and this -a plus 2b has to be 5. I mean, stop and think about it. Behind my pen, it's not going to be true if it's 4. It's not going to be true if it's 6. It's not going to be true if it's 1,000,000. The only way it's going to be true is if this is 5. And likewise, cover this up. How is this going to equal x, which is 1x? Well, behind my pen has to be equal to 1. It's not going to be true if it's 2 or -80 or anything else. This must be 1. So I'm going to set a plus b equal to 1, and -a plus 2b has to equal 5. And that's a system of equations, 2 equations and 2 unknowns, right? And we know how to solve that from algebra, right? You can do that by elimination, substitution, right? Okay, so one more time, right here, if this whole fraction is going to match this whole fraction, right? Well, I already got the denominators to match. How do I get the numerators to match? The only way is if this thing behind my pen must be equal to 1. And the stuff behind my pen here has to equal 5. So I set a plus b equal to 1. And -a plus 2b has to equal 5. Okay, so in this case, just add them up. A's drop out. 3b equals 6, which means b is 2. And substitute 2 back into here, I guess. A plus 2 equals 1, so a is equal to -1. So I found a and b. So x plus 5 divided by x plus 2, x minus 1 is -1 over x plus 2 over x minus 1. And that is exactly what I anticipated way back over here. Okay, so that's the major idea behind so-called partial fractions. Okay. All right, so I was just going to show you only one more problem. We still have almost 20 minutes, so we'll probably end fairly early. So I'll show you one just to whet your appetite, as it were. How do you do something like number 9? Okay, so I'll do number 9 in its entirety, and then I'll call it a day. 5x plus 1 over 2x plus 1, x minus 1. And by the way, as you might anticipate, so what if it's not factored? Well, you factor, right? Like 11, you would factor into what? 2x plus 1, x plus 1, or factor that and so forth, right? All right, so number 9. 5x plus 1 over 2x plus 1, x minus 1. So partial fractions, it says, can I change this so that it looks like this? Ignore the 1 and the 2 for a moment. Okay, I'm going to write 5x plus 1 over 2x plus 1, x minus 1 as that, no matter what the a and the b are. Let's pretend this came out to be pi. It won't, but even if it came out to be pi, this comes out to be square root of 2 over 2. That doesn't bother me. Because then when I change it back to an integral, they're both very easy integral. They're both some ln stuff. This one's going to involve a chain root, but no big deal. Okay. So a over 2x plus 1, b over x minus 1. What do I have to put for this pen? That, x minus 1, x minus 1. And what should I put for this pen over here? 2x plus 1 over 2x plus 1. You need a common denominator. All right, so here's the common denominator, 2x plus 1, x minus 1. Multiply all this mess out. Ax minus a plus 2bx plus b. Put together the x's and put together the non-x's, the constants officially. So these two have an x. Factor out the x, a plus 2b, x, plus parentheses, these two guys that don't have any x, negative a plus b. These two fractions have to match. Here's my original. Here's what I have. How can I get these to match? Well, the bottoms already match. Top has to match. So again, look at the numerator. Again, this is the coefficient of x, so cover it up. Whatever's behind my pen, can you guess what it has to equal? Since it's a coefficient of x. It has to equal this coefficient of x, 5. What does this coefficient or constant have to equal? 1. So I have two equations, two unknowns. Right? The game we're playing is, how do I get this fraction to match this fraction, right? Well, I already got the bottom the same. So how is this going to match? If this is going to match this, then behind this pen better be 5, right? It can't be 4, it can't be 3, it can't be 6, it better be 5. And if this fraction is going to match this fraction, then behind this pen, it better be 1. It can't be 0, it can't be 2, it can't be a million, it better be 1. So I set a plus b equal to 5, a plus 2b equal to 5, and negative a plus b has to equal 1. And once again, two equations, two unknowns, which I can solve from my Algebra 1 class. Right? So it looks like I just add them up. A's drop out. 3b equals 6, which means b is 2. And let's see, plug back in 2 here. 2 times 2 is 4. So I have a plus 4 equals 5, which means a equals 1. So a is 1, b is 2. And that's the reason why I put the 1 and the 2 here. So back in the original, the mystery is solved. I now change that to a 1 and I change that to a 2. Quick double check. If we put a 1 here and a 2 here, 1 plus 4 is 5, correct. If we put a 1 here and a 2 here, negative 1 plus 2 is equal to 1, yes. Double check. Now I'm ready to integrate, but that's the easy part. The hard part is to do all this partial fraction stuff. So the original integral, this funny fraction, I can now write as something over 2x plus 1 plus something over x minus 1. And I found out the somethings are 1 and 2. So my original integral is 1 over 2x plus 1 plus 2 over x minus 1. And now that's very easy. Okay, so integrate ln absolute value of 2x plus 1 times, let's see, times the opposite of what I would do if I differentiate, right? From calc 1, chain root, you have to multiply by 2. So when I integrate, multiply by half. Please make sure you understand the chain root. If you don't remember the chain root for derivatives, you're not going to get the chain root for integrals either, right? If I asked to differentiate this, when you got over here, you had to say, oh, times the derivative of the inside, right? Derivative of 2x plus 1 is 2. So when I differentiate it, I multiply by 2. Therefore, when I integrate, which is the opposite operation, I divide by 2 or multiply by half. Here, I don't have to worry about the chain root because the derivative of the inside is 1. So just put 2 ln absolute value of x plus 1 plus a constant. Again, to double check that, differentiate this whole thing. So what's the derivative of this, right? You would go 1 over, there it is, 1 over, and then by the chain root times 2, the derivative of the inside. Well, that 2 knocks out the half, so there it is. Plus, what's the derivative of this, right? You go 2 times 1 over x minus 1, and then again by the chain root times the derivative of x minus 1, but that's just 1. So I have it. And of course, the derivative of any constant is 0. So you know it works. Okay. Okay, so I'm just about done. I'll be finished in a few seconds, and then I'll take any questions, and if not, we'll just stop. But rehash this weird fraction. The question I ask is, can I write it so it looks like this? I separate it into separate parts. So partial fractions. I want to write it as some constant over that plus some other constant over that. If I can do that, it becomes a pretty easy integral. Okay? So I run through this partial fractions process, get my common denominator, work out the top, factor out the x, separate out the non-x, and I say to myself, this better be 5, and this better be 1. So a plus 2b has to equal 5. Negative a plus b has to equal 1. 2 equations and 2 unknowns. Solve, find my b and a, and then do this integral, and that pretty much does it. Okay. All right, so I'm done for the day, folks. So I've actually snuck in some of 7.4, so I'm a little bit ahead. We're going to be okay, it looks like, for now, unless I happen to fall behind or I get sick or my internet goes down. So it's nice to be a little bit ahead. But otherwise, I'm done for the day. So let me stop the share and see if there's any questions in the chat. And if not, then we can just call it a day. All right, any questions, please? All right, seeing nothing and hearing nothing, we'll call it a day. All right, so bye, everybody. See you next time. Okay, have a good day, everybody. Bye.